So, good evening to all respected dignitaries, honorable chiefs, esteemed speakers, distinguished delegates, and dear participants joining us from across the globe. It is a pleasure to welcome you all to day 20 of the 21-day International Winter School Training Program. Dexter's participation and enriching discussions over the past 19 days have truly strengthened the spirit of collaborative and experiential learning. Each session has offered valuable insights and meaningful knowledge exchange, broadening our academic and professional perspectives. As we begin today's program, we continue with the same enthusiasm, commitment, and passion for learning. On behalf of Just Agriculture, Indian Society of Agriculture, Science and Technology Research, and our collaborating partners, I warmly welcome you to this International Winter School Training Program under the theme Revolutionizing Agri-Systems through AI, Digital Tools, and Green Technology. This winter school brings together scientists, researchers, industry experts, and policymakers from across the world to deliberate on emerging innovations shaping modern agriculture. As we commence day 20, we look forward to an engaging and enriching session with eminent national and international resource persons from USA, Canada, Australia, Egypt, and India, who will share both research insights and practical experiences. We sincerely acknowledge the valuable support of our collaborating institutions, GNMKV Parbhani, UAS Raichur, Level University Canada, and ICR India New Delhi for their continued cooperation. With these words, let us proceed with today's session and reaffirm our commitment to building a sustainable and future-ready agro ecosystem. It is my great pleasure to welcome Dr. Anant Dinesh Rao Lad, Assistant Professor, Department of Entomology, Vasantrao Naik Marathwada Krishi Vidyapith, GNMKV, Parbhani, Maharashtra, to this esteemed International Winter School Training Program. Dr. Lad is a distinguished academician and researcher in the field of entomology with notable expertise in insect pest management and sustainable plant protection practices. His contribution to teaching, research, and extension has significantly strengthened the understanding of integrated and eco-friendly approaches in agriculture. We are truly honored to have Dr. Lag with us today, and we are confident that his valuable insights, practical experiences, and scientific perspectives will greatly enrich this training program and benefit our participants from diverse academic and professional backgrounds. On the behalf of Just Agriculture and Indian Society of Agriculture, Science and Technology Research, our collaborating institutions, and all the participants, I extend a very warm welcome to you, sir. We sincerely thank you for being a part of this prestigious program. Once again, very warm welcome to International Winter School Training Program, Dr. Lal.
Thank you, Rakshiji, uh, for giving me an opportunity to deliver this lecture. Just, I'm audible. Hello.
So you're audible.
Yes, yes. I'm sharing just my screen. Is it visible?
Yes, sir.
Okay. सुरुवात कुठे? Okay. Okay. Good evening and a very warm welcome all of you. I think this is the 20th day of this training program. You all people are very well enriched with a lot of knowledge with these modern technologies like digital tools, AI, machine learning. The today's topic is a digital tool for pest surveillance and integrated pest management, AI and machine learning approaches. This is the most important one because we already learned that agriculture and these modern tools, they are very useful for this all agriculture, and this is a very new sector. But if we concern with the pest surveillance and pest management, really these tools are very helpful for this pest surveillance and management also. In this lecture we see all these things. firstly, we must know that what is AI. Just if we see the this picture, this artificially intelligent, it is a field of computer science that emphasizes on the creation of intelligent machines which can work and react like a human. Means like a human, whatever instructions we are giving, or just they are able to identify what we are thinking, and according to that they make algorithm of that all data, and accordingly our like our human intelligence, they are giving the exact results. uh, then that Studipto Ghosh, they define this artificial intelligence is not a man versus machine saga. It is in fact man with machine synergy. Means they are very close association with the man and these machines. Uh, if you see the different uses of these AI in different sectors, no any sector is without AI. Every AI sector they require these AI and machine learning tools, and the most important one is the education. If you see from school child to our scientists also, everyone is using this AI, especially in education, for delivering any chapter for references, for research also. We are also searching for these AI tools like ChatGPT, Gemini, whatever it may be, the modern AI tools. Even though for giving one speech or for creating different models for different graphs also, we are using these AI tools. Then, no doubt, in case of business also, business analysis, everybody is using these AI technologies now, but till it is in under in initial phase. Then in medical science, it is the most that advanced use of these all these robotics and AI is in medical science, because very complicated surgeries made by this through by using this AI. And we people just talking about the agriculture sector. Though this agriculture sector is somewhat that slow in adoption of this AI, but since last 2 years, everybody is talking about this use of AI in agriculture. In case of especially our Indian Council of Agriculture Research, they start off one very good program, that is NAHEP, National Agriculture Higher Education Project. Under this project, they develop several these centers specially dedicated for this AI and robotics, machine learning also. Then banking sector is also, then heavy industries, and also some of the other sectors are also dealing with this. Uh, then why we need AI in agriculture? Because everybody is having good brain, everybody is having thinking power, and thereafter also we require this artificial intelligence. Uh, because in case of agriculture, uh, till we are self-sufficient in that food, but we achieve the food security, but we have to achieve this nutritional security also. To achieve this food security, we use plenty of pesticides. Thereafter, we use fertilizers, then modern tools also. But it deteriorates the quality of that foods and nutritional levels of the foods, that different foods. That's why, to increasing the demand of this nutritional food, we have to go with these AI tools, with the production of residue-free commodities. Then mostly to achieve this nutritional food security through this natural farming or organic farming, it requires plenty of labors. And in Indian agriculture, the most probable or most major constraint is the shortage of labors, because in natural farming we are taking uh, different mixed crops. Biodiversity is also different. That's why it requires so much labors also. And by using these AI tools, we have to detect the different weeds, different uh, different varieties also, and different crops also, and we can suggest some models through this AI which are suitable for this natural farming. That's why, to minimize the labors, by using these different sensors and different tools. uh, then climate change and weather uncertainty, this is the most important one. Since last 4 5 days, farmers are also very aware about this weather. They are planning their agricultural work or that agriculture calendar according to the these weather predictions. And very new tools are like some companies also like that SkyMed and our IMD also, they are giving very good weather advisories. On the basis of that advisories, we are undergoing our agriculture operations. But even though due to this climate change, there is so much uncertainty, and they are directly related to the pest incidents. That's why we have to deal with this climate change. And to combat these problems, this AI is very helpful for developing different forecasting models and different that weather forecasting also. Then precision farming. This is the most important one because timeliness is the most important one. Then timeliness is also that economically, socially also viable, and that's why we have to do everything with this precision farming. And to make decision timely, this AI is also helpful. Then we are talking in detail about the pest surveillance and pest detection, because through our manual survey there might be some error in pest and disease diagnosis, but through machines, if we given the correct data, then definitely that will detect almost 90 to 95% correct detection. And then in irrigation and water management, already since last 5 decades we are using that micro irrigation systems. But if we these micro irrigation systems we joined with these smart tools like yeah, definitely what is the water requirement of that particular crop, what is the water requirement of that particular soil, what is the water requirement for that particular crop and particular plant also, we can easily uh, find out due to this by using different sensors. And also we give the correct irrigation systems, it will helpful for our water management possible water management strategies also. Thereafter, market linkages and price forecasting. This is the most important issue in front of our farmers, because they are very ahead with production of different that commodities, but the market is the major problem. When they produce plenty of production, and at the same time there is a very ups and downs in markets. To combat this by using the data of the past several years, through this AI system, we can forecast the what will be the prices of different commodities, what are the different export and import policies of our country, and it will helpful. Then customized advisories of best services, then policy implementation and monitoring also done by using these AI tools. Also, AI provides accurate and timely information regarding our crops and weathers. Already, we already discussed this one, and it will improve definitely the crop productivity and reduce the risk and improve the income of the farmers. And ultimately, it will increase the that whatever the income of our farmers. And ultimately, our honorable Prime Minister is also talking about doubling of the farmers, and it will helpful to achieve that goal. Then in case of climate change, definitely due to this climate change, that increasing CO2 levels or whatever it may be, drought or any that high rainfall, it directly influences or it directly correlates with the pest population. And ultimately it can create some issues in our food security also, because in due to this pest and disease problem, definitely there will be if we cannot able to manage this pest and diseases within their spread or in primary, definitely it will be hamper our yields, and it gives very adverse effect, and ultimately it can make a problem in our food security also. uh, then many of the farmers still especially in North India, those in command area, these farmers, they are using these flood irrigations, then and excess use of waters also, and it creates different problems with soil, with crops also. Then hazardous or indiscriminate use of pesticides, is their pest is present or absent. With a periodical cycle, farmers are using pesticides, and their doses are also indiscriminate, because they are not using the proper or recommended doses as per CIB. They are just that dumping the pesticides in the fields, and it will create problems with the environment, and that pollution is also most important one. Then same with the herbicides, though we are using this herbicide, but it can be directly affecting the that microflora or microbes of our soil, and it deteriorates the soil fertility also. That's why we have to use these tools. Then before discussing all this pest detection and pest surveillance and integrated pest management, just we look after the history of intelligence, that artificial intelligence. Just we are talking artificial intelligence since last 2 3 years, but this concept was put forth in 1950. That can machine can think. This can be this can be just think in 1950, but in 1956, that special John McCarthy coined the term the artificial intelligence, and this is the 1956 is the birth year of artificial intelligence. And thereafter, in 1959, computers became faster and affordable, and in 1961, uh, the first robot unit was held in 1961. Thereafter, the first chatbot, that is Eliza, was introduced in 1964, and then the term Internet of Things, especially in development phase since 1999 until in 2017, real application of this AI was already started. This is brief about the history of artificial intelligence. Then why this pest management needs artificial intelligence? Why due to our conventional pest management strategy we cannot manage this pest? First one is I have already talked about that labor intensive operation. From the pest surveillance to the pest management, pest surveillance, pest detection, all these things done to this labor. Traditional pest control demands extensive manual labors for everything, for seed treatment, for then for application of these pesticides, then the detection of the pest, scouting of the different pests, taking data, then again that analysis of the data manually. These require too much manual labor, and ultimately it will cost higher. That's why to minimize the time gap between the pest detection and pest management strategies, we have to go through this labor intensive. Then even though we are using with skill manpower to identify the pest, but till there is due to this human error, there are too much gaps between the identification between the identification. That's why we have to take care of that also. uh, in case of identification, even though we are giving several trainings to this that pest scouting or pest surveillance field staffs, but thereafter also due to these trainings they are unable to identify 100% in field levels. That's why and that identification is most important, because it's like a base of an building. If the base is not so much strong, that building can be collapsed any times. That's why if we solely depends on this manual pest detection or pest identification, definitely one time our whatever that our pest surveillance system and pest management system may be collapsed. That's why to identify these to minimize these identification gaps, we have to use this AI. Then need of precision. Whenever that pest detects within a time limit, we have to give correct advisory to that particular farmers, and we have to emphasize, or we have to whenever there is pest crosses the ETL levels, within that 6 hours or within the 10 hours, we have to start with the implementation. That's why the most important is the precision, and to achieve this precision we need AI. Then if we see the impact of or the growing challenge of pest management, pest destroys near about 20 to 40% of the global crops. Means the major role of losses is these pest and diseases. Each are kind, the cost is near about 70 billion in losses, and it ultimately threaten the our food security worldwide also. Then that traditional limitations are also most important. That is, the manual monitoring is very slow. It requires from any person that maybe take observations in field condition, that may be fitted in whatever it may be system. Thereafter there is analysis, and we cannot able to real time advisory, or we cannot disseminate these advisories within a stipulated time. And already these are very slow, labor intensive, reactive, detecting problems only after significant damages occurred. And after significant damage is done, then whatever that remedies were, or whatever the recommendations giving for this pest management, that are having the no use. Then pesticide overuse creates the resistant pest population, and it ultimately harms the ecosystem and drives up operational cost for farmers also. Even though if the pest is under ETL, even though thereafter also we are dumping that pesticides in fields also, and application of such pesticides without achieving the ETL level, that will create the problems with our ecosystem, and ultimately it will hamper the activities of natural enemies. And if you see, the 98% of the pest population was controlled by these abiotic and biotic factors, and only 2% of the pest population was controlled by using these crores of rupees of these pesticides. And if these biotic and abiotic factors, they are doing their jobs very well, then there is no any problems. But even though farmers are just giving this pesticide, and also due to repeated use of this pesticides, there is several examples of that development of resistance in pest population. Recent example is that BT cotton. Even though that BT that pink boolworm, it ultimately attains the resistance against this BT also. And then several examples like DPM, then Helicoverpa parmigera. It gives changing temperature and changing weather patterns triggers more frequent and severe pest outbreak, demanding the smarter solution. It means climate and that pest population buildup has a very close association. Ultimately, there is some if CO2 level is increasing, definitely it will increase the rapid development of their life cycles also. And in Indian conditions, especially we are dependent on these monsoon weathers, and in especially in rainy season, there is always there is at least 15 days or 10 days or 20 days dry period. And ultimately, due to this dry period, there is a very rapid buildup of this sucking pest population. Uh, and it will create the that suddenly accelerate the pest population also. And sometimes in this year, especially in Maharashtra, there is heavy rainfall in this year, that ultimate there is continuous rainfall of near about 22 days, 25 days, and it will encourage the lepidopteran pests also. That's why we have to also consider this climate acceleration. Then that late detection. If we detect the pest after whatever it may be, the significant losses are occurred, then there is no use of such type of detection. And very good example in Maharashtra is in 2008. There is heavy havoc of this Spodoptera litura on soybean crop, and pest is not properly detected in 2008. That's why, and after attaining fifth star or sixth or fourth star, then that much reporting is yeah, very late. And due to that late reporting, farmers and state agriculture department unable to manage these losses, and near about 7 government has to give 555 crores towards compensation to the farmers also. And this is the just due to this late detection of the uh, this pest. And unable to give the timely advisories, and it ultimately, due to this late detection, no doubt there is a crop losses, but ultimately, to manage this some that bigger insects, we require some higher doses of insecticide. We have to use some harmful insecticides also. It will create the environmental risk also. Ultimately, crop losses was done. We are spending on plant protection, and ultimately environmental risk also. It will results into losses in billions. That's why we have to go for this AI. Screen ka? Just 1 minute. I think screen is on share. Again, mistake था. Then AI powered automated pest detection, and that eyes that never sleeps, because the AI is already working throughout 24 by 7. That's why they are the never that closing eyes, and we can rely on these tools also, and they are helpful for continuous monitoring by using different cameras, sensors, collect heat movements, and sounds data through 24 by 7 in field conditions also. And also for analysis, previously it required so very long time, and within that time, uh, as we delay to analyze and to detect the pest, definitely it will keep responsible for losses also, and results crop loss also. That's why through by using this AI or machine learning processes, massive data sets for accurate pest species identification was also developed. Then targeted response. That system recommends precise treatment, reducing pesticide overuse and protecting yields also. It means that if we have the some 8 to 10 plant protection tactics applicable for that particular crop in that particular season and that particular time, but from that 8 to 10 plant protection tactics, we have to choose the correct plant protection method or plant protection tactics, and that all must be compatible manner, and it cannot be done with the that humanly within a stipulated time. That's why by using these innovative tools, we can just target the response by choosing correct method through timely. Then there are several success stories of cotton, sugar cane, especially in case of the CICR peoples. They have developed that AI with pheromones and detected bollworms and early cutting pesticide use while increasing the yield significantly. Due to this early detection, they have given timely management, especially the pest like pink bollworm. Because these bollworms, if they enter into the bolls, thereafter they are very difficult to manage. That's why their early detection is in rosette flowers. And if we detect these rosette flowers through this uh, AI or AIML or through these cameras, it will helpful to manage this pest very early. And in pheromones also, if we the several moths are captured in pheromone traps, and that images can be captured through these cameras. Definitely on that images we can identify the pest, and before that egg laying, we can manage this pest by through mass trapping, or by using the modern tools like by using the biological control tools of like parasitoids, trichogramma. Thereafter, drones. No doubt, to spray several or hundreds of acres through manual spray, it is very harmful and hazardous to human beings also, and it creates very difficulty to use such pesticide, especially in crops like sugarcane, then some fruit crops. it is very difficult to spray that such type of crops. And by using these drones, we can easily spray the crops, and within a very short time, it will be helpful to manage this pest within restricted areas of hotspots, and we can manage, or we can suppress this pest to spread over these pest free areas. Then uh, sometimes while taking these manual observations, generally insects are very active in morning sessions or in evening sessions. But sometimes our that whatever the scouts, field scouts, they can take observations in mostly in whatever it may be the afternoon hours, because they have to complete their works. In such cases, they cannot able to identify the pest within stipulated time or on that crop also. But if we use these modern AI tools, and the crop was under surveillance 24/7, definitely they can detect all activities of our pests, and it will helpful to analyze or to detect that pest. Then that if we stop the infestation before the start, it means whenever there is a start of infestation, definitely we will combat that pest by uh, spreading on other area. That's why we have to collect data, and what kind of data we require, just weather pattern, what type of weather may be in coming days. Then what are the different pest life cycles, is there any generation is completed, or is there any that forewarning that possibilities of developing another generation or population buildup. And then historical data of last 5 years, 10 years, what is the pattern of pest buildup and crop stage and previous outbreak records also. Such type of data, if we given to these AI tools, definitely it will helpful, and all this data can be analyzed within a very short period, and it gives good proactive action, that is precision intervention, minimizing the pesticide use and crop damage. It means if we detect the pest before it spread, definitely it will save crores of rupees of pesticide, and ultimately it can be helpful for our environment also. It can save our ecosystem also, and ultimately the crop damage, and increasing the income of our farmers also. There are several case studies that AI driven intervention reduced the moth population by 1.5 billion, dramatically boosting the almond production. This is one. Thereafter, that is automated pest detection. Again, the same things here. Advanced AI systems leverage the cutting edge technology to monitor agriculture environments, continuously providing the unprecedented accuracy and speed in pest identification. It means already due to these modern sensors, by on the basis of these different images and different behavior and different crop damage symptoms also, they can easily detect the pest. To detect that one, that multi sensors are required, that cameras, infrared sensors are now developed. Then acoustics are also devices that can be helpful on the to identify the different pest activities through the noise also. Then capture the comprehensive pest activity, and all this data can be collected 24/7 in real time. And the machine learning algorithm process hit that is signatures, movement patterns, then wing beats, frequencies, sound profiles for precise identification, and then that all these having real-time processing, instantly using cloud-based AI processing, and classify all this data, and what type of pests are now present, that can be easily outcomes. And due to this early detection enables the target intervention, dramatically reducing the labor cost and uncertainty pesticide applications also. Then these AI and IoT devices also, that smart and portable, all these devices are very efficient, uh, and as farmers are using in coming days this device, definitely there will be cost reduction also. There are some lightweight models are also developed, then on-site detection, and their detecting accuracy is nearly about 98%. Then they are having the now connectivity, real-time connectivity is also is there. GSM or GPRS communication send data to the cloud platform for instant decision support also. Means some I will give some examples also. Some apps are very good. They are giving real time solutions also. Again, within a same time, they are identifying the different pests and diseases, and on same time, what are the that control measures that should be done. They are giving these such type of decisions also. Then another thing is uh, that Scout Labs, they are giving the realizing the pest monitoring with AI and IoT. These are the IoT digital traps. They are capturing daily high resolution insect images. Thousands of images are captured by this camera and analyzed by AI and expert entomologists. It will helpful for such type of traps are also helpful for our decision making. Then precision provide accurate pest pressure warnings, enabling targeted pesticide application, and definitely it gives the sustainable impact. Then cutting edge, it is already we are repeating that one. Then precision pest control strategic enabled by this AI, it can be helpful uh, to optimizing the treatment plans. Optimizing the treatment plans, AI recommends that precise timing, location, doses for interventions, dramatically minimizing the chemical use and environmental impact. It means due to this AI, if we capture one image, it definitely by machine learning, we can able to identify that image of that. Is it that pest is perfect or easily diagnosed, or that disease is easily diagnosed. Thereafter, what time that pest is present in that particular field and at what location. It means it will helpful to detect the hotspots of pest also, and what is the that pest level present in that field condition at that level and in adjoining areas also. And on the basis of that, what type of doses of interventions we have to use, and it will definitely minimize the chemical use, because we have to target the highly hotspots for this pesticide use, and it will save the environment also. Then integrated biological controls, if that combines pheromone traps, beneficial insects, and natural predators with remote sensor monitoring for sustainable management. For example, if we use this pheromone trap must be used especially in case of Lepidoptera. If the that adult population present in the field conditions, under such circumstances, we have to use these pheromone traps. If the larval population is present in field condition, there is no use of these pheromone traps. Means to make the decisions of using these biological control tools, we have to go with this AI technology. Then, if the beneficial insects are present in field condition, then also there is no need for chemical interventions or any biological. That it will helpful. Then what is the exact population of these natural predators and beneficiaries. If this population is plenty available in field condition, then also there is no need of this any harmful effects or harmful tools. That's why it will be helpful for sustainable management of our agriculture. Then that most important is the integrated pest management framework. It enables the comprehensive integrated pest management with real-time data, feedback tools, and adaptive strategies. And ultimately it will helpful to protect our ecosystem also. And also most important thing is that the pollinators, most of the pollinators, they are very active, especially in night hours or in yes, but due to these harmful chemicals like neonicotinoids, these pollinators may be hampered. Then integrated this artificial intelligence into integrated pest management, smarter and sustainable pest management. I have already talked with the biological controls methods like predator, parasitoids, and parasites, their activity and how we can engage this predator parasite. If their prey is available in field condition, then and then we have to go for these predators. Which pest is there? Accordingly, that pest specific predators we can release. Then pest specific parasitoids we can release. If the pest is especially if the pest is lepidopteran pest and we are deploying the parasitoids of any other insects, then it cannot work. That's why we have to correlate with the what type of pests are present in field condition and what that parasitoids we are releasing. Then different parasite cultures, then different EPF cultures also we are using. For sucking pest, we are using verticillium licheni. That's why we must know the what type of sucking pest is present and how the climate is then. Then we can go for that particular EPF. For soil arthropods, we are using metarhizium anisopli also. It can amalgam with this IPM technology. Then that cultural practices like crop rotation and resistant varieties that are also through this AI. Then AI integrates all methods intelligently. Already I have given some examples like that. If we use these different methods, especially in case of integrated pest management, we are using biological methods, cultural methods, mechanical methods, physical methods, legal methods. But among all these methods, each method is having near about a set of 20 treatment, 100 treatment, 200 treatments. But and from that 200 treatment, if the 10 to 20 treatments they are applicable for that particular crop or that particular stage, but from that 20 table, it is not possible to implement all these 20 treatments, and it is not also cost effective. That's why we have to choose one or two just treatments, and it will help with it can be done with the help of this AI. Then targeted chemicals. If the pest is sucking pest, and we are going for different the chemicals which are not uh, recommended for that particular pest, but farmers are using such type of chemicals and spending lot of money on this plant protection tag. That's why if the pest is sucking pest, then we have to go for a particular systemic effective and systemic insecticides. If the pest is having very initial stage, then we have to go for some green label insecticides also. That's why to make a decision of which type of chemicals we have to use that real time, and that can be done, that such decisions can be done with the help of these AI tools. And ultimately it will reduce the pesticide resistance development, then protected beneficial insect population, minimizes ecosystem disruption, and some innovable examples are already we have discussed. Then Scout Lab innovations are there, that affordable solar powered digital traps with cellular and AI connectivity results uh, 10 to 13 times cheaper than the traditional competitors. Then another thing is that drones inspections inspect all services, deploy drones for hard to reach areas, dramatically increasing the detection accuracy and coverage. Ultimately, especially in case of sugarcane, most of the farmers they are using these drones, and orchards also they are spraying with the help of this drone. Then some farmers in Maharashtra, they are combining this AI with pheromone traps to manage bollworms, reducing pesticide overuse while increasing the yield significantly. Especially in our KVK Baramati in Maharashtra, they are using this sugarcane with AI. This is the one of the very good successful example of AI in agriculture. Now our government of Maharashtra is also giving more emphasis on these AI policies, and already they have spent near about 500 crores for this AI, and it will be helpful for in the industry transformation. AI adoption is accelerating rapidly, shifting pest control from reactive crisis management to predictive precision-based prevention strategy that benefits farmers and environment also. Then most important thing is that benefits of AI in pest management. Artificial intelligence deliver transformative advantages across environmental, economic, and operational dimensions of modern pest control. That precision detection dramatically increase the accuracy in pest detection, species classification. There are several species of Spodoptera, several species of Lepidopteran pest, several species of the same order, but that can be easily classified by using these modern tools, and eliminates this that goosework and enables the targeted response. Ultimately, there is a environmental protection is achieved due to that decrease in pesticide use, environmental contamination, health risks for human, wildlife, and beneficial insects also. And ultimately, if we minimize these chemicals, labors, ultimately it will minimize the cost also. And automated monitoring system reduced manual labor requirement translate directly to into substantial cost reduction. And data collaboration, enhanced data sharing platforms enable community collaboration, creating collective intelligence for superior pest control technique. And if all these things done in a stipulated time, ultimately it will increase the production also, and ultimately the doubling the farmer income target. Some of the that AI based mobile applications nowadays used in agriculture, we see some examples also, especially just one especially these Kisan GPT is also uh, working, and this AI chatbot for farmers of that special natural language support for crop care, their weather pest, then plantics. Uh, it is well known for everyone. They are doing very well. AI powered crop disease diagnostic using the image recognition, and it is very successful application. By using these plantics app, most of the farmers are using by detecting these there are different diseases, nutrient deficiencies, and pests also. Then Bharat Agri is another personalized crop advisory using AI soil test recommendation. Then Krishi AI is also for pest disease detection, weather and crop planning. Krishi Bazar is also for market and prices related. Then Agri app for crop advisory. Then again, since last year, uh, our government of Maharashtra and all four universities, especially Vasantrao Naik Marathwada Krishi Vidyapit, they we developed the Mahavistar AI, and nowadays in Maharashtra, this is a very popular AI tool, AI app for the farmers. It provides farmers with real-time crop-specific advice, weather updates, then disease detection, and also it will helpful for government scheme information in both vernacular language like Marathi and English also. Then Krushik app provides 50 days village level weather forecast. Then Fasal app crop stage based advisory weather forecast. That NPS, National Pest Surveillance System, is also working very good in national level, developed by NCIPM peoples. Uh, then uh, Harnessing AI in CropSap and HotSap, revolutionizing the crop and horticulture scheme. uh, that artificial intelligence is most important, especially in case of uh, CropSap. CropSap is a crop-based surveillance advisory system. It is a pilot project implemented in Maharashtra since 2008, and ultimately, as time it is the first example of using this, especially this IT in agriculture, and this project received national award for in 2012 and Prime Minister award for in 2015 for this crop pest surveillance to the government of Maharashtra. In this year system, our state agriculture department field staffs, they collecting data from the field. Uh, they're collecting data from the field, and within a short period that data can be uploaded on university servers, and whatever the research associates and our scientists in university, they can analyze that one with the help of these softwares, and within 10 to 12 hours period, whatever the real time advice that can be disseminated to that particular persons, and also given to the state agriculture department, also which villages they can process the ETL, which are nearing to the ETL, that can be easily detected through this one. And in this structure, they are using machine learning advanced algorithm analysis vast agriculture data sets, especially image data sets are used. Then computer vision is also most important one, that is helpful for image recognition technology, and identifies the plant health issues, especially pest infestation, crop maturity with remarkable accuracy and speed, and especially the nutrient also. Then Internet of Things, connected sensors and devices, helpful for smart farming ecosystem that monitor and respond to environmental conditions real times. Then precision agriculture, this is already somewhat repetition, but it can be done through this CropSap AI integration. And for that one, CropSap is the dedicated software developed by our IT, Maha IT. Then AI in pest disease management protecting crops smarter, it means already we have covered this one also. Then these are some of the examples of AI-driven innovations in horticulture, like intelligent monitoring, resource optimization, post-harvest excellence. Then it is all about the Plantix. That is the it is Plantix is a German startup company developed this Plantix app. This multi-language plant disease and pest diagnostic app. They use the P8 algorithm, identify the pest diseases within a few seconds, and critical information like symptoms, trigger, agrochemicals, as well as biological treatments provided to users. Weather information is also given, and planting was enabled in specially launched in Telugu language, but now it is in 16 global languages and 18 Indian. And Plantis now can identify over 385 crop diseases. It is some examples given by this Casmin Fernandez in 2020. Then they give the services of free crop diagnosis in WhatsApp. Then diagnosis and treatment also. Then challenges and that road for this AI, that data privacy and compliance is the most important one. That establishing secure framework and meet the regulatory requirements across the region. This is the most important. And data privacy, that what type of data we are uploading, that must be we must keep the data privacy also. Then the interdisciplinary collaboration, because whatever that identification of pest, collection of images, that can be done by the field staff. Then thereafter the real classification of that images and creating different models, that can be done by these scientists, especially entomologists and pathologists and some extension people. Then after the whatever that machine learning part or whatever the analysis part or algorithm part, that can be done by these IT peoples, ITians, or that IT experts. That's why the interdisciplinary collaboration is very necessary to success this AI. Then equitable access, ensuring small scale and resource limited can adopt AI tools affordably, and it requires continuous data sets and continuous innovations, because the climate is changing, that pest scenario is changing, pest buildup is there, new pests are also emerged. Then some of the natural enemies are also emerged. There is sometimes there is a development of resistance in pest. There is also advancements in pesticide use pattern. Then some of the new molecules are introduced, some of the old molecules are harmful molecules, we have to minimize. That's why continuing innovation is also required. Then critical priority is also most global impact depends on the democratizing access to AI powered pest management technologies. Then current obstacles for that is the till date we cannot have the sufficient data. That's why AI system demand extensive training data sets and contact updates to accurately identifying emerging pest species and diseases also. Nowadays, just few images are also available, but AI models, they require thousands or lakhs of images in different angles and different stages also. For example, in case of Lepidoptera, there are four stages: egg, then larval stage. Again, in that larval stage, there are 4 to 5 instars. Again, pupal stages are different. Again, adult stages are different, and we require thousands of images of that particular pest. Again, same pest having the different species also. That's why we have to go with the huge collection of this data. These are the major obstacles nowadays, and that's why government is giving some projects to collect data for these yeah, development of this AI. Then integration is also complex. Seamless connection with existing farm management software and that diverse IoT platform remains critical for widespread adoption also. Sometimes in field conditions, there is no availability of uh, especially that internet availability is also most important problem. That's why seamless connection is also most important. Barriers to into then privacy concerns, data security requirements, initial investment is also very vast. Then cost challenges, some growers, particularly that smaller operators, are they are unable to spend such type of higher investments. The next generation includes advanced behavioral analysis, multi-sensor fusion technologies, and fully automated pest control robots that will revolutionize the agriculture practices also. Uh, Already by using this artificial intelligence and machine learning, empowering global food security, increase yield, protect crops from devastating losses while optimizing production. ultimately it will reduce the chemicals protected. It will protect our ecosystem. Uh, Ultimately, we can achieve our goal of to sustain our ecosystem, to minimize losses of our farmers, and ultimately the goal of doubling the farmers' income. It is all about this, whatever it may be the AI, because nowadays, in especially in case of agriculture, this EIML technology is in very little stage, or in that very child stage. That's why in initial phase, whatever information with me, I can deliver that much information. Again, day by day, we will go ahead with some recent information, and definitely in future eras, this technology can create uh, very good for our farmers. Uh, with this, I'm very much thankful for Just Agriculture for giving me an opportunity to deliver my views regarding the AIML pest detection, integrated pest management in front of you. I'm also thankful for all the participants, and especially the Just Agriculture team, Sakshi ma'am. Again, thank you very much.
Thank you very much, sir. Participants can please drop their questions in the chat box if any. Since there are no questions from the participants' side, sir, I would like to ask a question from you. Like, how can AI and machine learning tools be practically integrated into field level IPM for timely and scalable pest management, especially for smallholder farmers?
Yes, yes, this is most important one, because especially in Maharashtra, our farmers having very small holdings like 2 acre, 1 acre. But there are very some models. The farmers, if they are using drones, we can map that small area also. Even though we are able to that map areas like 10 hours, means 1/4 of 1 acre can be mapped by these drones, and we can use these drones in small areas also. Again, for pest detection, different cameras can be used, and that will given data to our AI based softwares regularly. On the basis of that, early pest detection is also possible, especially this AI tools can be used in small farming, especially for irrigation purpose, because the different sensors are used for this one, especially in sugarcane. Our Baramati peoples, they are working very good with these AI models. Again, some pheromone traps, with smart pheromone traps are also available, that are also helpful to detect the pest very easily uh, by using such type of then some that mobile operated apps are also developed, like Mahavistar, then CropSap AI, then NPSS app, that will help to real-time detection of the pest, even though in small holdings also, and giving that advisories within a few seconds also.
Okay, sir. There's another question from my side. Like, how can AI and machine learning based pest surveillance systems can be validated and scaled across diverse agroclimatic regions while maintaining the core principles for integrated pest management?
This is also most important question. For this, that integrating, we have to, because this divert that climate change, there are very different types of climates is also available, and for such climates, we have to collect different data of these different climates, and on that particular climate, which pest population can be built up, that can be predicted from relative humidity, then temperature pattern, rainfall pattern, and that particular season and crop stage. It will helpful to integrate the what type of pest can be built, or what type of diseases can be built in near future. Thereafter, by collecting different image-based data, uh, these image-based data and that pest and disease symptoms and that particular crop stage, that can be integrated with this weather. It will be give the clear picture of that pest identification or pest forecasting also.
Okay, sir. Thank you. Thank you very much for joining us today, sir, and for delivering such an insightful, informative, and forward looking session on the topic digital tools for pest surveillance and IPM, AI, and machine learning approaches. On the behalf of Just Agriculture, Indian Society of Agriculture Science and Technology Research, our collaborating institutions, and all the participants of the International Winter School Training Program, I extend our heartfelt gratitude to you for sharing your valuable time, expertise, and scholarly insights with us today. Your enlightening deliberations on AI driven pest surveillance system, digital monitoring tools, predictive analytics, and machine learning based decision support models have greatly enhanced our understanding of modern integrated pest management approaches. Once again, sir, we sincerely thank you for being a part of this prestigious program and for contributing so significantly to its success. Your valuable contribution will surely leave a lasting impact on the all of the participants and will guide future research, innovation, and practical implementation in the field of digital agriculture and sustainable plant protection. Thank you once again for such an enriching session, sir.
Thank you very much.
Thank you, sir.
Just one.
Our next guest will be joining us in few minutes. So, moving ahead with the program, it's a great pleasure to welcome Dr. Ilga Mercedes Porth, Associate Professor in Functional Genomics, Laval University, Canada, to this esteemed international winter school training program. Dr. Porth is a renowned scientist in the field of functional genomics with significant contributions to understanding gene function, molecular regulation, and the application of genomics in improving agriculture and biological systems. Her research integrates advanced genomic tools with innovative approaches to address key challenges in the sustainable agriculture. We are truly honored to have Dr. Poth with us today. We are confident that her global perspective, cutting edge research insights, and interdisciplinary expertise will greatly enrich this today's session and provide valuable learning to all of the participants. On the behalf of Just Agriculture and the Indian Society of Agriculture Science and Technology Research, our collaborating institutions, and all the participants, I extend a very warm welcome to you, ma'am, and we sincerely thank you for joining us and sharing your expertise with us. Thank you, ma'am.
Hello, can you hear me?
Yes, ma'am.
Okay, I will start sharing the screen. Okay. Sorry, I have a problem. What is my... Can you see my slides?
Yes, ma'am.
Thank you very much. Is the sound okay too?
Yes, ma'am.
Thank you. Well, first of all, thank you. How much time I have? I'm sorry, I want to make sure.
Approximately 1 hour, ma'am, till 7.
1 hour, okay. Well, let's see. Well, anyway, thank you very much. To you, it's afternoon, evening at your place. So for me, it's early morning in Quebec, in Canada. And I want to thank you for inviting me to give this presentation. As it was introduced, I'm working in genomics mostly, and I'm working in forestry. So forest trees have also value, for example, in agroforestry. And they are bred in Canada to obtain genetic gain in growth, so they are plantation forests as well. So this is what I will be mostly focusing on. I am not talking about natural forests here. So the title of my talk is related to genomic prediction for phenomics-driven breeding. And specifically, we are interested in translating genomic information into biological function, and I will come to this towards the end of my talk. In general, we are facing a global crisis that affects forest. As you might know, there are problems in drought exposure that is increasing and is projected to increase by the year 2100 even more. So this is pictures mostly of conifer forests, because conifers are so to say, the working horse of tree breeding in Canada. They have been widely outplanted for the forest industry. The other thing that is a challenge is the changes in the phenology of the pests and pathogens in relation to climate change, so that makes trees more vulnerable to those pests and pathogens. So we observe already more frequent outbreaks. And the other thing is we have problems with forest invasive alien species, insects, but also pathogens. And especially this is noticeable in urban forestry context, where trees are outplanted to provide some ecosystem services and to shield from excessive heat. But we can notice even here where I'm living that we have problems, especially with the emerald ash borer, So all these ash trees have to be replaced and cannot be planted anymore. The other problem is with elm trees. There we have the Dutch elm disease problem in Canada and also in the US, actually. Another problem is oak wilt now that is becoming more a problem also for natural oak forests, but also for oaks that are widely planted in urban contexts. And generally, we see tree lineage, this is related to conifers, that is projected to be moving northwards, or they are climate niches, their projected climate niches are moving northwards. So for the conifers to persist, and this is an example of black spruce, they would have to move forward. But of course, trees cannot move with that speed northward. Then actually it's projected that the climate niches are changing for them. So there's some application that is being under investigation and slowly implemented, which is assisted migration in helping forests or forest trees actually to find the optimal niches into the future. So as I mentioned, I'm working in genomics. So we're interested to advance forest genomics projects in a way to help and get and obtain social and economic benefits for the forestry sector. So this could be related to preventing disease establishment, which is a short-term aim, but also long-term aims are to provide climate-adaptive forests and plantation forests. So when you outplant forests, which have to be on the landscape for many, many years or tens of years, then you need to make sure that into the future they are resilient, both to climate but also to pests and diseases. Otherwise, you have a lot of economic losses. And this is where our work is focused on. And for today, I would like to give you some information about how we go about forest tree breeding. First of all, I will introduce the conventional breeding versus the genomics-informed breeding. I will give a brief overview of the conventional tree improvement cycle so that you can have some background on this if you're not familiar with this, which might be a little bit different than crop breeding. And then I will do the comparison or about the implementation of genomics for selection in forest trees and how this actually has advanced the tree improvement, especially in terms of cutting the time frame of tree breeding. And this is due to something called genomic realized kinship matrix. So genetic markers are used to establish these genomic relationships for the breeding program and then use this in genetic parameter evaluation and actually be able to get more accurate genetic parameters such as heritability of quantitative characters. Then I will talk also about how the linkage disequilibrium in forest trees is perceived. So linkage disequilibrium is basically the non-random association of genetic markers that can be leveraged to infer relatedness, but also to infer association of genetic markers with quantitative traits. So basically to identify causal variance underlying trait variation. And I will give you some information about the measure of linkage disequilibrium along the genome, how it was perceived like 20 years ago, and what we find now in the genome when we have tools such as whole genome sequencing available to us. And the other information that I would like to provide you is how can we leverage genomic information more substantially to also gain insight into the biological function of genetic variations. So not to work only with neutral markers as it has been done in the past, but also have some better understanding of the genetic variation that underlies phenotypic variation and their biological function, actually. And to do this, I will provide you one example that we do for phenotypic prediction actually in fast-growing trees. And at the end, I will give you some information where we are in the field of forestry and genomics and how can we better implement genomics in forestry. So as I mentioned, I will give you some short introduction to the tree improvement cycle. So one of the things to consider here, and I can use I will use a highlighter, laser pointer. So one of the things that's important to consider here that we have not that advanced breeding programs as in crop breeding. So they are maybe second or third generation, rarely fourth generation breeding programs here in the Western Hemisphere. I heard that in China they have more advanced breeding programs in conifers than we have here. So we call this also shallow pedigree. So at the beginning stands the selection of so-called plus trees from natural stands that are usually evaluated by showing superior growth patterns such as advantageous growth architecture, fast growth, and this is further evaluated by something called progeny tested. But at the beginning, the forestry breeder is collecting vegetative or reproductive material from the natural stand, plants this in a so-called breeding arboretum or clone bank, and then performs controlled crossing, mostly either open pollinated progeny or full siblings. And these descendants or progeny are then tested, and based on their genetic characters and phenotypic characters, then the tree breeder goes on and to reselect those parents. These reselected parents are then used both ways. They are entering the first generation breeding, or they're concluding the first generation breeding cycle, where these reselected parents are again collected for grafting scions. So that means vegetative material. So basically then you use the material of which you know already the quality, let's say in growth rate or tree architecture. And then you do directed breeding, directed pollination. So you basically pollinate the female reproductive organs with pollen from selected males. And then you go into the second generation breeding, where you again establish the breeding arboretum, do progeny testing, and progeny testing is then usually done over multiple sites to disentangle the effect of genetics and the environment and the interaction between the genetics and the environment. On the right side is the production cycle, where in the first phase you already pre-selected your parents, you establish them in something called seed orchard, and then you do mass pollination in the seed orchard. You select the seeds, you process them, you test them, you register those seeds, and with the registered seeds, tested seeds, and processed seeds, you go into a seedling production. This looks like this. And then you use those seedlings in outplanting. Outplanting, again, you outplant them in various environments that are suitable for these seedlings, and you perform your reforestation. And you do the same thing with the second generation breeding. You established all of this again, and the cycle continues indefinitely, more or less. But as I said, we are only in the second and third generation mostly here. So this is where we stand in forest improvement. So this is the cycle again. To sum this up, you start out from the natural stand. You have your plus tree selected. You do the breeding by constructing a structured pedigree. So either open pollinated families or full SIP pedigrees. And then you test them on large areas and in multiple areas as well. And then you test the progenies of these breedings. And then you apply magically quantitative genetics with which you are able to rank the parents, reselect the parents, and go into the next cycle of the breeding program. So now what are the innovations? As you know, traditional breeding, or as maybe I have conveyed you now, traditional breeding, and in this way, tree improvement programs rely on the creation of a structured pedigree, known as the line of descent, which is very time consuming. And then the progeny testing comes with it. That is, again, very time consuming because you have to wait multiple years to have an idea how well the progeny is performing, and which gives you an information how well actually the parents are suitable for breeding. So when you now implement information that is based on genomics or on genetic markers, and ideally they are spread evenly over the genome of a certain species, like I can use an example. We use spruce or pine trees here in Canada or in the United States. We tend to cover the genome quite evenly with genetic markers. So these genetic markers or genomics-based approaches, they have shown unprecedented opportunities. So what they can help you to do is, first of all, to maintain accurate individuals' contemporary and ancestral pedigree, which means you have some information also about the genetic diversity in the population, because in forestry, maybe as opposed to crop breeding, people are interested to have a high genetic diversity. And this is really important going into the future, because I told you the trees are there for many, many years, and they have been adapted to a lot of environmental pressures like biotic stress, pests, pathogens, but also changes in humidity, and so drought stress, but also temperature rising. So genomics can handle this information, but it can also, it is also able to track a specific trace causal genes. Like I said, you have this information of the dual nature of DNA. First of all, you can track the ancestry in a pedigree, the contemporary one, but also the ancestral one. And that makes it less shallow, actually. And then you can also track some information of biological meaningfulness of genetic variation as it relates to phenotypic traits. So genomics or genetic information can generate this reliable genetic information in a relatively reduced time frame. And it can help you get the estimates of heritability, so the genetic control of quantitative characters, and facilitate, therefore, the estimation of the individual's genetic worth for further selection. And I'm talking about not only the parents, but also the pedigree as we go into the future breeding programs. So how predictive accuracy works in general, maybe you are familiar with this. If you're not, I'm giving you a brief overview here. So there is something called model training. So model training or establishment of a predictive model is based on using your whole population, leaving out a certain percentage of data, so of individuals that you do know actually the phenotypic data. You have genotyped everything, the phenotypic data, but you leave them out in the prediction. So this could be 30% of the population or 20% of the population. And you build a training on something called the training population, so on the remaining 70 or 80%. So this predictive model is trained on known data. And then you use this to identify these relationships between genotypic markers and phenotypic variation. And then you do prediction. So you use this established predictive model to predict the remaining 20 or 30% of the population where you do know in reality the data, but you don't use those data. You use only the genotypic data. And you use the model to predict using this genotypic data now the phenotypic data. And then you compare the model's prediction to the actual observed outcomes in the new data, which you already have. And then you evaluate this, and then the degree to which the predicted values match the actual values is actually is called the model's predictive accuracy. So, and this helps you to rank individuals in the end and to select superior individuals, and then you can also get rid of inferior genotypes or individuals. And this is shown in this scheme here, so something that we call genomic selection. This is an example that has been done for two important, economically important tree species in Canada. It's the Douglas fir species that is outplanted in the western part of Canada, and white spruce that is outplanted with different ecological varieties over whole Canada. So western Canada into eastern Canada, where I'm living. So you do this, as I mentioned, you do this predictive equation establishment, and then you have not only the predictive accuracy that is, this is relatively high for Douglas fir because we used an important exome capture array that actually focused also, that was established based on transcriptome data that gave you already some indication of the biological worth of the genetic markers that you pre-selected. For white spruce, we have a bit of a lower predictive accuracy because this was based on genotyping by sequencing that used more agnostic markers, so to say, that are probably less relevant for the actual trait variation prediction, but it was relevant enough to follow the line of descent, so the relationship in the population. So here you see that the predictive equation evaluation gives you not only the predictive accuracy, but can also help you to eliminate individuals that are less superior, and then you move on with the superior individuals and integrate them into subsequent breeding programs. So this is how genetic markers enable us to actually trace back the line of descent. So you have here the 3 generations from grandparents, parents to offspring. So you identify here based on, this is the orange segments that we are following here. You basically trace back the identity by descent fragment here, or IBD, that 2 individuals are sharing, and to trace this back basically to the second and third generation. And that gives you some information that, I don't see anything here, about the coefficient of kinship that is important to actually estimate genetic variation or genetic control, such as heritability. And as you know, the heritability quantifies the proportion of the variation in a trait that is due to genetic factors. So this kinship coefficient is really important input for the variance component decomposition in the models, and to be able to calculate this genetic control, which is the heritability of a phenotypic trait. So here you see a table that actually exemplifies what we can do with genomic information as opposed to having only pedigree-based relationship. Pedigree-based relationship is just simply, and this is an example of half-SIP families, where basically the individuals have the same mother but different fathers, where the coefficient of relatedness is estimated to be 0.25. I hope we agree. So this is the estimation of the coefficient of relatedness or kinship coefficient for half-SIP individuals is 0.25. And here we have examples of two sets of half-SIP families termed A with 4 pedigree, just semantic to make the matrix not too overburdening. And then again, 4 individuals from family B. And now, if you, as opposed to just using pedigree-based information, assumed information of relatedness, you actually implement genetic markers and they actually create a matrix that has different values than just 0.25, because actually this is estimating the real relationship, the so-called genomic-based relationship between the markers, and you get different values. So they can be a little bit lower than 0.25, but they can also be higher because they capture also the ancestral relationship. And astonishingly, you do not really assume between those two families that they are related. So basically, in the pedigree-based relationship, assuming there is no relationship between those families, so you will put values of 0, but when you use genetic markers, you see as actually values popping up. So basically, there is some relationship possible, and here you have even 0.25 as an example between individual A4 and individual B1, so that, or even higher, 0.35. So there is actually a relationship between these individuals. So this can also be exemplified in this network. So here on the left side, you have examples of multiple sets. So I think it's around 90 sets of half-SIP families. Again, half-SIPs share the same mother but different parents. And this is exemplified and called the contemporary pedigree. So this is what you assume that the relationship is actually between the individuals. Now, when you're turning towards genetic markers, you can actually construct a connected network between individuals, which is also, again, I want to come back to this matrix, which is actually being able to integrate these values as well into a network construction where you have a real connection. So yeah, you can see there is one family that's not connected, but actually, apart from that, all of them are somehow connected, and there is just a hub actually of connections here in the center. So this is due to the fact that genetic markers can now help you not only uncover the assumed contemporary pedigree and now more accurately actually also estimated the contemporary pedigree by genetic markers, but also the ancestral pedigree, how these individuals have been connected. And this is due to an understanding of population genetics, because the underlying logic under this is there has been ancestral gene flow between those individuals. As you know, probably, that forest trees, especially conifers, are wind pollinated. So the pollen can travel long distances. So it is not surprising that there is actually a real connectedness between those individuals going back to the past. And this is what you actually can see in this network. Another example here, so we have looked at these half-SIP families where you can uncover other values as well that are deviating from the 0.25 line that you see here, that you assume when you just look at contemporary pedigree as assumed contemporary pedigree. For 4 SIPs, the same pattern used for 4 SIPs, which means they share the same mother and the same father. You can also see a broader peak, so you get different values around 0.5, which should be the contemporary pedigree that you're assuming this. And very interestingly, and this is what is related to what I told you before about the wind pollination between individuals in conifer forests or other, this is actually an example in poplar. This is true for deciduous tree species too. You're assuming actually there's no relationship in natural population, especially when you sample at longer distances, as we did that in poplar. So several kilometers distances, but you can also recover there's actually some sort of relatedness between individuals that are further apart. And you can uncover this only by using genetic markers. Then I would like to talk with you about the linkage disequilibrium. So as I said, linkage disequilibrium is basically due to the non-random mating of individuals. And as you can actually see this along the genome. So this is an information that was given like more than 20 years ago in a seminal paper by David Neal and Otto Savolainen. They were really the pioneers in this. But in this case, so there was in forests, we didn't have this genome information, and what we were doing here, they were looking at candidate genes, and what they showed here, that there is a lot of recombination in the genome, and this is on the level of candidate genes. So the linkage disequilibrium is already decaying within a gene, because this is basically the distance of within a gene is about 3,000 base pairs. But when we do whole genome sequencing, we can see interesting other patterns that we see actually long-range linkage disequilibrium in certain areas. And this we found is mostly linked to something called structural genomic variation. So these are long-range haplotype blocks where we also found genes that we identified associated with climate variables, so adaptive genetic variation that is co-inherited. And you can find this in so-called haplotype blocks. So again, I want to pay attention. There is some sort of linkage disequilibrium that extends beyond this 3,000, but we found it around 9.5 mega base pairs. So this is 3 kilo base pairs, and this is in the order of mega base pairs. So interesting features that can be identified by genome sequencing. So when we do breeding in conifers, at the beginning there was the tendency to do marker-assisted selection, and this marker-assisted selection was meant to be based on genome-wide association studies. Except for some simple inheritance traits like this one, which is poplar leaf rust resistant, where we can identify, so to say, the gold nuggets, which are quantitative trait loci or quantitative trait nucleotides that are repeatable associations over years. And they are more single markers. In forestries, when it comes to growth traits, we are not able to use this because growth is a polygenic trait where it is underlying are multiple, maybe thousands of markers with small effect sizes. So we cannot use GWAS, and this is why we turn to genomic selection. The other things that we are interested to look at when we do breeding, when we select for a certain trait, how another trait is responding, right? So we have to estimate something called genetic integration coefficients, so we can see how one trait relates to another. If there is something called a trade-off where there is a negative relationship, this relationship could be good, but if we want to have a positive relationship, for example, we are selecting for growth, but we also want to have increased resistance to a certain pathogen or to a certain insect pest. So to have a negative relationship, this would not be off. So you can also use the genetic relationship matrix to get a better estimate of this genetic integration or genetic correlation network, and also estimate response to selection. So when you select for certain. So this is an example where we used no pedigree. So this is basically using the genetic relationship matrix to estimate genetic correlations. These are wood traits for fast-growing biofuel poplars that could be used in agroforestry as well, just to give you some example. So what we have to do, we have to do some provenance testing, first of all, to select individuals that are superior in traits, and then we sequence them. We did something called allele mining, and then we further looked into candidate genomic regions to test some genomic editing, mostly not to plant our GMO trees, but to verify the genetic variation that has an effect on a phenotypic trait. And then we can do something using genomic selection and genomic prediction. I will get back to do in short. So we can use this, as I said, this genomic resources and genomic relationship matrix that we can build also, as I showed you before. I will show you this here again. So this is actually the population that we used for this, because we can uncover other relationships between individuals to estimate this heritability estimates. I don't show you that list here of these traits, but also the genetic relationships between traits. And this is related to what I showed you before, to have some idea about any trade-offs between traits and phenotypic integration. So for example, what I show you here, this is some sort of a negative correlation between lignin content and cellulose content, and this was actually quite deemed advantageous because we want to breed for poplar trees that are more amenable to decomposition of the secondary cell wall, so we can extract more easily cellulose for biofuel, bioethanol production, and at the same time, when we would breed for higher cellulose, we found that also the amount of lignin goes down, which is good because lignin is actually very protective over the microfibers, which actually is diminishing our capacity to extract the sugars for bioethanol. So this was a good result. And more recently, we were looking again using genomic information to identify something called variants that are disruptive in the production of proteins that are found in this layer of secondary cell wall decomposition. So these are all known genes in the network of secondary cell wall composition in poplar. Again, our focus was here with a view in the future to identify variants that would give us some information about interesting cell wall, secondary cell wall characteristics that will allow for a better extraction of the sugars in the cell wall. Because as you know, the secondary cell wall is not meant to be deconstructed. It's actually a protective layer for the plant cells. So humans are searching to decompose this, so that goes against nature. But we can find in nature actually some variants that actually have these beneficial characteristics. And this was shown and published in 2013 by Van Holm, which is a natural variant here in the HCT gene that is involved in lignin decomposition. So they found individuals harboring this variation, this defective variation, actually are more amenable to secondary cell wall destruction because they have a more favorable lignin decomposition. So this is a scheme that would ideally be used in using this variance in tree breeding, where you actually introduce this variant that is usually rare in a natural population, but introducing in a breeding population in poplar. So in this case, it would be the black poplar that is outplanted in Europe. And then you basically increase the frequency of this variant and produce homozygous individuals. So we have actually looked in this on a wider scale than for 24,000 disruptive variants across the Populus trichocarpa genome. Populus trichocarpa is actually growing in Western Canada and all the way from Alaska down to California. And we had over 1,000 individuals, whole genome sequenced individuals at our disposition. We had also transcriptome data, so gene expression data for 300 individuals approximately from this population. And we were hunting for this rare disruptive variants that we found in this population and the associated individuals. So we were interested to see if there is an effect on the overall gene expression when these individuals have those variants. And we looked at two different sites, so one in the US and one in Canada. And we tested for significance between changes in gene expression in those variants when those variants were in homozygous state. So that means both alleles were defected in the individuals versus the expression of these genes in individuals where they didn't have this defective variants at all, or when we have heterozygous status of individuals, so one allele is defective, the other one is regular, versus individuals that have only regular alleles. And as you can see, in this case, so these are the two sides, and this is the homozygous individuals versus the heterozygous individuals. That is way more spread in the changes in gene expression where homozygous individuals are. So basically, the idea here is to see if there is an effect in overall gene expression. So it could be upregulated, but mostly downregulated significantly. And if we introduce these variants one day in a breeding population, what this could give us. So we are at this stage. And the other thing is now what we are looking for, and this is again in Populus trichocarpa. So please, this is not a structured pedigree. Again, this is all data from natural populations. And we use this information to predict phenotype. So here we use all variants that we actually found, and also again transcript data. And in this shows you information where we are trying to combine genetic information with transcriptome information and see if we integrate, if we are looking at genetic variation alone or transcript variation alone or a combination of both, what it gives us in being able to predict the quantitative traits. So this is an example of a lignin trait. Again, as I mentioned before, lignin is okay. Sorry, I have a problem with my. I have to connect to the power plug. One moment. So should be good now. So this is what we wanted to see, if there is any improvement or what it gives us information if we combine genetic variants together with transcriptome data. And here in this heat plot, you can basically see the outcomes. So the more bright the color, the higher the predictive accuracy. So up to point and above 0.8. So this translates into 80% of predictive accuracy. And this is an example for a lignin trait. As I told you before, lignin, we would like to have advantageous lignin trait to be able to deconstruct actually the secondary cell wall in Poplar for biofueling. And it is known that a higher percentage of syringal lignin is advantageous as opposed to guaiacil lignin. So we are looking at this trait. So this is the explanation. So we started out from millions of SNPs and tens of thousands of transcripts and boiled it all down to a couple of transcripts. So this is the number of transcripts versus the number SNPs and how we did this. So we used a variable pre-selection method that is based on the variation of the phenotypic data. So in this case, we were able to handle a more manageable amount of data. And then the next thing was we used this information and did structural learning. We used the Bayesian modeling, and then we quantified those relationships. We used it to find consensus edges, and then we trained a final consensus model on the full data set. And this is what I'm showing you here as an example, again, for the same trait. So here you can see how it's presented. So on the left side, you have all the genetic variation, also called SNP data, which stands for single nucleotide polymorphism. In the middle, you have data that are related to transcript data and their interactions as well, shown by those arrows here. So you can see some interaction between SNP data, some interaction between transcript data, few interactions between both of them, and then how all these interactions are relating and are important for predicting the syringin lignin trait at a predictive accuracy of R square 0.83. So again, you have here the direct connections of SNP data to the phenotype, the direct connection of the transcript to the trait, the phenotype, the syringin lignin, and you have all the interaction terms as well. So the interactions and everything is shown here. So we found 25 interactions directly predicting SNP phenotype, the transcript here termed RNA for ribosomal nucleic and then we have also the interaction between RNA and so we have 10 interactions. We have also interactions between SNP data. So one of the things that we came across when we applied genomics in phenotypic prediction is that we are still missing some information, and this is due to the different layers that we know actually are related in dictating phenotypes, or when you have phenomic data. So you can think of anything that you can measure actually in a plant. So we have, of course, the layer that is dictated by the DNA level, so genomics. And then you have the next level, because basically the paradigm is to go from the DNA level to the RNA level to the protein level, and you don't go the other way around. So it is always going in this direction. And then the transcripts are important to sequence your proteins, and the proteins, the enzymes, make your metabolites, and those metabolites then are expressed in certain traits that you can measure. Basically, you can measure them even as a proxy using a multispec or hyperspectral data when you think about using sensor data, for example. And this is actually what we are more and more looking in forestry as well. And here comes also the necessity with all this data to use artificial intelligence to manage those data. So we are looking currently into this. So we don't have the analysis finished yet. I cannot provide you this for conifers such as white spruce. We are still working on it. But to sum this up a little bit in relationship to understanding forestries, the genomics, the underlying genomics, to understand also the biological functions of genetic variants, so how they actually directly affect the phenotypic traits, we have to understand the tree species. So this is an example actually of a tree species that is not yet a matter of extensive breeding, which is another popular species, not Trichocarpa as I mentioned before, but Tremuloides, which is actually the most widely occurring tree species in North America. In North America, I'm speaking with Canada, about Canada, US, and also Mexico, because Mexico is also belonging to North America. And actually, this tree species is, can you see, coast to coast, basically in Canada. It's also in Alaska, there are populations, and goes all the way to central Mexico. So we have studied this, and first, before we even think about introducing this in any measures of assisted migration, tree breeding, you have to get a handle of understanding the tree species. So this tree species is really, really very interesting. First of all, to understand it, we had to generate extensive genetic resources. We had to understand the phylogeographic history of this species, basically where it comes from, how it actually spread across the continent after the last glacial maximum, to understand the genetic variation, and actually to understand how into the future this species is gonna perform. So in this sense, we were able to look at the genetic structure, and we have several papers now published on this. The other thing is this species is very interesting because it can reproduce sexually. So you can basically maximize the genetic diversity, but it can also propagate through clonal reproduction, especially through root suckering. And we recently learned actually that underground there is sort of a network of roots that can even spread from clones that you don't find a remnant, so those stems anymore, they are gone, but they can, after a disturbance like fire, they can resprout. And you can increase the genetic diversity, or the species can increase the genetic diversity based on that. The other thing that is very interesting to the species is that it can be a diploid and a triploid, so it has 3 times the chromosome the chromosome count versus diploid only. And we found, and others as well actually, that this occurrence of triploids is associated with some restrictions in the environment, so mostly drought stress related. So there could be some adaptive advantage to this, but we are in collaboration with the University of Berkeley, we're actually looking into this more specifically in common garden experiments. Another thing is what we did a small greenhouse common garden experiment as well to look at the phenotypic plasticity in the species, and what we found is that the most southern populations here indicated in Mexico show very high plasticity if you expose them to elevated temperature and elevated drought stress. So this was very interesting too. And then last not least, we did population genetics, landscape genomics, and identified thousands of candidates that are interesting for looking into adaptive genetic variation in the species. So to finalize my presentation here, where we are in forestry. So there is one part is the breeding, but there is also the sustainable forest management and how genomics can help. So one of the things is we can identify diagnostic genetic markers. So this can be to disease resistance. I showed you one example in a poplar leaf rust. So we were able to identify diagnostic genetic markers, but you can also not only looking per se at the tree, so at the host species, but you can also identify diagnostic genetic markers when it comes to a pest or pathogen, and we worked on this as well. So you can do this from both sides. We appreciate in genomics that the costs for DNA sequencing are ever increasing, and the bioinformatics tools are getting more sensitive. The analytics are way better than years back, so this helps a lot as well. So our genome assemblies are way better. We have reference genome quality. And the other thing is, of course, more and more we have to implement phenomics on different layers, especially using sensors, so we can actually measure phenotypic variation across huge landscape areas. Because I showed you in the beginning, actually, this provenance testing or these tests are outplanted in vast areas, and you're not going there to do manual identification of pigments, for example, or metabolites and everything. Everything can usually, when you establish a model in phenomics, you can actually correlate it to a certain degree with spectral imaging. Some of the challenges that are still remaining are we still struggle with understanding the missing heritability, and one of the things that has been proposed is actually to look at other genomic features. I showed you an example of structural variation where you have blocks of haplotypes which explain the variation with adaptive traits. So this is really very promising to look at this. But for this, you have to do long read sequencing, and it's really a challenge still in conifers. We can do this in trees with smaller genomes like poplar, which have just a portion of the genome size of conifers, because conifers are in the range between 20 and 40 gigabase pairs, whereas poplar has only 450 megabase pairs. And the last challenge is implementing all this knowledge and turn it over to forest management so that it can be really accurately applied. And the other challenge, the last challenge, is especially when we're looking at high throughput phenotyping, is data management, long-term storage of the data, and accessibility. And this is my lab that has been working with me over the last years. And here I have some literature for you if you're interested to read more into this that I mentioned. Thank you very much. I think I went exactly 1 hour.
Thank you very much, ma'am. Participants are allowed to drop their questions in the chat box. Since yet there are no questions from the participant sides, ma'am, I would like to ask a question from you. Like, what are the key challenges in applying genomics phenomics-based predictive breeding under diverse environments? And how can these approaches be adapted for resource-limited breeding programs, particularly in developing countries?
Yes, I think the major challenges would be like monetary investments, I would say. However, if investments are done, I think the gap is actually narrowing because you can get so much information through phenomics, so high throughput phenotyping that could actually be closing the gap to this. I see this like this. Genomics, well, you can still do phenomics breeding without genomics if you look at the pedigree-based assessment, so that is still done, and we ourselves did that actually, where we didn't have access to any genetic data. So that's still doable, I would say. But I really feel that actually I feel that the phenomics part using hyperspectral data or multispectral data and other data, LiDAR data. I think it's actually closing the gap, I would say. Yes.
Okay, thank you, ma'am, for giving response to my question. Thank you very much, ma'am. Sorry, for delivering an insightful, engaging, and intellectually enriching lecture on genomic prediction for phenomics-driven breeding, translating genomic information into biological functions. On the behalf of Just Agriculture and Indian Society of Agriculture Science and Technology Research, our collaborating institutions, and all the participants of the International Winter School Training Program, I extend our sincere appreciation to you for generously sharing your time, expertise, and scientific perspectives with us. Your presentation clearly demonstrated how the integration of genomic prediction, high thoughtful phenomics, and advanced analytical tools is reshaping modern plant breeding by effectively linking genotype to phenotype. Once again, we thank you for being a part of this prestigious program and for your valuable contribution to this success. Your expertise your and perspectives will undoubtedly inspire students, researchers, and professionals to pursue integrative genomics phenomics approaches in their future research and breeding initiative. Thank you, ma'am, for a truly excellent and enlightening session with us. Thank you, ma'am.
Thank you very much, and I want to extend my wishes, and I wish you a good workshop. Thank you.
With this, moving ahead to our next guest, it's my great pleasure to welcome Dr. Neela Samantare, co-founder and chief AI officer, Stealth AI Startup Canada, to this esteemed international winter school training program. Dr. Samantare is an accomplished expert in artificial intelligence and advanced digital innovations with strong experience in building AI-driven solutions for real-world applications. His work at the intersection of AI, data science, and emerging technologies highlights the transformative potential of intelligent systems across sectors, including agriculture and allied domains. We are truly honored to have Dr. Samantare with us today. His industry-driven insights, entrepreneurial perspective, and global experience are sure to provide valuable learning and practical exposure to our participants. On the behalf of Just Agriculture and Indian Society of Agriculture Science and Technology Research, our collaborating institutions, and all the participants, I extend a warm welcome to you, sir, and we sincerely thank to you for joining us and contributing to the success of this international program.
Yeah, thank you very much, Sakshi. Thanks for the introduction. And good evening, everybody. I am Nilabdi Samantare. I'm not yet a doctor. So basically, thanks anyway for that, Sakshi. So I am a CEO and co-founder of an organization called Cobot Incorporation here in Canada. And prior to this, I had spent a good amount of time with IBM Global Services, wherein I worked in multiple industries, including the agriculture industry. And I was also with CSM Technologies for the last 5 years prior to this, where my key contributions were, and among the other industries, it was food and agriculture as well, where we did a lot of tech interventions using emerging technologies, especially artificial intelligence, analytics, advanced analytics, satellite imagery, and drone and similar technology interventions we had done. So I'm going to share a slide. Please let me know, Sakshi, if it is visible, okay?
Yes, sir, it is visible.
Okay. Yeah, thanks, Sakshi. I will just stop sharing my video and then we can get started, okay? Video, I mean my video, not the slides. Okay, I'll run through the slides, and then whatever questions you might have, you can ask me, and I'll be very happy to answer that. So as I said, I'm Nilabdi Samantray, and today we are going to talk about the farming and different tech interventions in the global food system using the emerging technologies. So this is where I stay. Right now I'm here in Regina, Saskatchewan, which is called Prairies. So Prairies are one of the three provinces which are adjacent to each other: Alberta, Saskatchewan, and Manitoba. This is what is called the breadbasket of Canada. That is where almost 60 to 70% of all the food, especially wheat and few other crops, they grow out here. So this is that area. This is pretty white at this point of time. And I think today, if I look at the temperature, it's close to -20 right now. This is what it happens after March. So, after March, April, this is what is going to be, how it's going to look. Okay. This is the agenda which we are going to catch up today. Current challenges in global agriculture, overview of different agricultural technologies, precision agriculture or smart farming, digital tools, AI applications, biotechnology, genetic innovations, sustainable tech, maybe case study. We talk about a case study and future outlook and recommendations. So the global agricultural challenges, we have the population is going to be 9.7 billion. Right now it's 8 billion by 2050. And then slowly that's when it's going to be the peak, and then slowly it comes down. But till then it keeps on growing. There is a lot of climate change happening. Probably there is only 2 countries where we say carbon negative. Interestingly, one of them is in the whole world, more than 200 countries, and only 2 countries which are carbon negative. Bhutan is one of them, our neighbor. And degradation of soil and water resources, food security issues, malnutrition, labor shortage in many countries, and post-harvest losses. These are the major agriculture challenges globally. So technology as a game changer, yes. Technology has been doing and can do a lot of things: increase productivity, real-time monitoring, decision-making, reducing environmental footprint. As I said, Bhutan was an example. So when we say environmental footprint, basically the carbon footprints, it's like carbon emission. So 3 times whatever the carbon emission is happening in Bhutan, there is 3 times more natural plantations and natural resources which absorbs it. So 3 times more is getting absorbed. Okay. Improving farmer income and livelihoods, enhancing supply chain, building climate resilient agriculture, and democratizing the access to agricultural knowledge. This is what are going to be a game changer for agriculture. These are the modern vertical farming technology that we have. Vertical farming, I'm sure there would be some sessions which would be already spoken about vertical farming, and we will quickly touch base. And I think we were talking about hydroponics and aeroponics some time back in some of the sessions, I guess. IoT sensors, LED grow lights, climate control systems, aquaponics. So aeroponics are where you don't have like hydroponics are where the plants are on the water. There is no soil out there. Similarly, aquaponics and aeroponics is where it is air. So air and aquaponics is water. Local food distribution and community engagement. So these are the different modern farming technologies. Drones are being used for surveillance and spraying of pesticides as well as fertilizers. GPS and GIS mapping for field management. It's by using the different GPS and GIS mapping system, we are also able to ensure that a particular plant doesn't have disease or pesticides or any of those things. Like from image processing of satellite imagery or drone imagery, we are able to detect that, and then necessarily intervention is being done. Soil sensors using different RFIDs and sensors. The moisture monitoring can be done, which is being done in many places. Yield mapping and monitoring systems, automated irrigation systems, VRDs for inputs and reduction of the losses while increasing the yield is what precision technology is all about. IoT and smart farming, it is all about connected sensors for real-time data collections, weather stations and microclimate monitoring, livestock tracking. So I will tell you one of the examples of livestock tracking and health monitoring. So one of the projects in IBM was about sorry, it was not IBM, it was in the organization after IBM, where we were doing prawn farming. In prawn farming, so that once you fit, they are done in the ponds, so you can do prawn farming in the lake or the prawn or different, there are different ways how you do that. There are very large ponds. So by fitting the sensors, we were able to detect there are many things that happens. The color of the prawn, it changes, whether it is yellow or white, or what is the nature of the water, if you need to change some water or there is some intervention required if the prawns are falling sick. So all of that was being able to done using the sensors, the camera feeds, as well as the quality of the water, based on which the pH content and other aspects were being able to detect, and necessary intervention was being done. So this is one of the livestock tracking or health monitoring interventions that was being done. And and there are other livestock monitoring that is being done where remote management is done by whenever there are say we have monitoring of chickens, or they are monitoring of sheeps. So those kind of monitoring is also being done, and the cloud-based analytics and predictive alerts that is being sent across to the different tabs and mobiles, where the farmer is able to see what is happening. This is an example of one of the AI interventions that we had done in CSM technologies, whereas we were able to detect the disease through computer vision and AI and machine learning algorithm. By looking at the specific image, then processing the same, we were able to figure out whether it is a fungus, it is a bacterial, or it is a virus, what kind of disease that is, whether it is a wheat rust or a powdery mildew or a leaf spot, mosaic virus or nutrient deficiency. So whatever it was, there was a certain percentage of confidence, like it says with a 98% confidence, the machine says this is wheat rust. So those interventions in very large fields and actors, by looking at the images only in the image processing, we were able to do that. So this is what we had implemented as one of our tech interventions. Then again, biotechnology intervention, that is modern agricultural technology, where we are able to do the gene editing. CRISPR gene editing is done, which also you can make it stress resistant to sun or excessive rain and things like that, which damages the crop. So you are able to do that by using biotechnology interventions. Biofertilizers, then there is biofertilizers are basically the biofertilizers and microbial soil solutions, where we are not using any artificial fertilizers, but the natural fertilizers that is being used. And biofortification is to make it more resilient. The crops are being made more resilient. And precision breeding. So we spoke about precision agriculture, as well as there is the precision breeding also, and tissue culture that we come up for different plant breeds. Robotics and automation. Robotics has been used in different parts of the world, and where we see autonomous tractors, robotic harvesters, where the specially deployed robots they are able to pluck some, maybe whether it is specific apples or specific fruits, it is able to pluck, and the robots is also able to pluck out the weeds from within the agriculture. Automated grading, dairy products, warehouse monitoring, warehouse automation. So we see that a lot. Say, for example, in Alibaba has one of the largest warehouse automations. It has a lot of cobots. Cobots are collaborative robots. And then there are dairy products where we also do automated, so milking can also be done. So this also makes labor more efficient, so that they are able to work on the areas where the specific skilled labor is required, more effective labor is required. Blockchain traceability. So there is this pretty famous IBM use case, farm to fork, where one of the customers sitting in a New York restaurant was able to figure out by asking the server from where the fish has come, and they were able to trace it back to a specific pond in Indonesia to a specific farmer. So that is the kind of traceability that can be done using blockchain. So this was done, one of the very famous use cases of IBM. The other use case was the Colombian coffee, which if you are having a Colombian coffee, drinking it, say, in Bhatinda in Punjab, or Bangalore in Karnataka, or say in here in Regina in Canada, we are able to trace it back to the specific source from the Colombia, from where the particular coffee has come. And this is another very popular use case and case study from IBM. So while you look at the different case studies of blockchain implementation, so I had spent around 13 years in IBM. So that is where different multiple use cases using blockchain and traceability was being implemented. Digital extension and advisory service, mobile advisory apps, video learning platforms, SMS service. So this is something which all the farmer communities, they are able to get it across, and I think more and more farmers are benefiting out of this. And most important is the last mile connectivity that is required so that every farmer across the globe, in every country, they're able to reap the benefit out of that. And I think there is a lot of digital extension is being done in India as well. And of course, it's being done in China, it's there in Canada, in US, and many countries it's being done. Renewable energy is one of the major areas of interest by many because of the cost optimization, as well as the long-term energy solution. Of course, there is solar dyeing units, biogas from waste. So waste products are converted to biogas, and that is being used. Wind energy is, I think, prominently started using across India as well. Apart from many countries, India is also using a lot of wind energy. Solar irrigation pumps are there. Electric vehicles are becoming very common across the globe. And energy efficient cold storage, lower carbon footprint. These are the key reasons why renewable energy is become more and more important for agriculture. Vertical farming and CA, so controlled environment farming. This is what we spoke about earlier, where we make sure that the environment is controlled, how much of light and how much of air and everything is being passed. Hydroponics and aeroponics is what we spoke about. And I think the speaker prior to me also, she also spoke about it a bit. LED lighting, year-round production, urban farming. So how you can do year-round production, you can go for multi-crops. Urban farming, and 90% water saving is being done by vertical farming and CA. And high productivity is also done. Success stories. Israel has a pretty success story of how they were able to convert a lot of deserts to good irrigated farms. Drip irrigation was started in Israel. So these are one of the examples where we see success stories. Desert farming. So there are many examples across the world, but why I picked Israel is because they were able to do desert farming and drip irrigation, which was very unique at when this got started. Now it has been done in many places across the world, including India. But back then they were the one who were pioneers. So they were able to convert a lot of large deserts into very good irrigated farms. Strong R&D ecosystem, agri-tech exports, policy support, and water efficiency is what we see from that story. Success story of India, 50 million farmers on digital platforms already. We spoke about it. Pradhan Mantri Kisan or PM Kisan, ENAM, Kisan call centers, drone spraying, soil health cards, and FPO empowerment. This is all being done in India across. It's no more in plan. It's already effective and being done. Barriers to technology, yes, there are barriers. There is some of the technology, it's pretty high cost. If you have hundreds of acres of land to be covered using drone and drone pilots and all, it can sometimes come costly when you are regularly flying the drones to monitor. But you can go for alternatives also, satellite imagery and stuff like that. And low digital literacy. This is another area, connectivity gaps, small land holdings, awareness gap, technical support issues, policy challenges. So these are some of the barriers. However, there is also enabling is being done. So the enabling technology adoption is subsidies. A lot of subsidies being provided by most of the countries. In India also, most of the states, they have state level subsidies, and there is also central level subsidies. Public-private partnership, training programs, demonstration farms, custom hiring centers, infrastructure improvement that's being done across pan India right now, and role of FPOs. I think fixed price offices and shops. So those are also got a pretty good roles out here. Future technologies on horizon. Quantum computing. These are future technologies, but already we are already seeing some of the interventions and implementation being already there. Quantum computing, nanotechnology, synthetic biology, swan robotics, 6G connectivity. These are all future. Digital twins are already there. It's no more future. It's already being implemented. Brain computer interacts. Building sustainable food systems. So tech, traditional knowledge, climate smart agriculture, circular economy, cold chain waste reduction, regenerative agriculture, carbon monitoring, and biodiversity conservation. So some of the building sustainable food systems. This is how we are building. Key recommendations is for investing more in R&D, both public and private sector, farmer-centric technologies, rural digital infrastructure, enabling policies, public-private partnership, capacity building, and inclusive access. Conclusion, technology is not just an option, it is an imperative for the future of agriculture. So there was a very famous line spoken by one of my colleagues. She said, I think one of my connections, she said, technology cannot be undone. You only have to get onboarded. Like, mobile phones, they came some 20, 25 years back. So you cannot undo it, and you cannot ask people to go back to landline phones. You have to get onboarded, and that's what the whole world has become onboarded on that. On similar lines, every technology which comes, sustainable and good technology, it has to be accepted and adopted. AI being one of the new technologies. See, AI is not new. So just to give you a background, AI is since 1956. It's more than 70 years old. Why it has become relevant today? Because there is a common implications of the same. See, emerging technology is not a new technology. Emerging technologies are those technologies which becomes relevant to the industry. AI has become relevant in the last 2-3 years because now everybody uses ChatGPT, right, to get answers. Even the Google that you use, it's now generates generative AI answers are being generated. So it's there in your smartphone. It's there everywhere. Similarly, even in agriculture. So all the questions that you ask in agriculture also, it's AI is being generated. So it has become commonly used, and that is why it has become emerging. Till it is being used by common man, men, women, children, they don't become. Now, for example, if you want to see a Netflix, Orange is New Black season or anything else, they are all curated in AI. So the way you respond to a particular season, that if somebody says, if there are a lot of comments in one season that a particular actor should not have died. In the next season, even if the actor has got 5 bullet wounds, would have survived, because that is how the feedback has come from the viewers, and they want, so they create the next story. AI helps them to do that. So there is, of course, there is plus and minus, both the pros and cons of AI, but most of it is pros. Cons will be there, but as I think one of the McKinsey report had said, there will be 115 million job losses because of AI. And the same report had also predicted there would be, I think, 170 million or such new jobs created. So there is always a two sides of the same coin. Just like when the Windows computers came, so a lot of people thought there would be a lot of job losses, but there were more jobs ever created in the history of mankind than before having the Windows. Exactly on the similar lines, tech interventions and AI in agriculture is going to further optimize agriculture and solve the world food and agriculture issues more than anything else in times to come. And it's already being done. Let's work together to make agriculture smart, sustainable, and prosperous for all. Thank you. So I'm open to any kind of questions that you might have. So these are some of the references. Okay. Now I will just close the presentation. And I'm open to any questions anyone has.
Participants can drop their questions now in the chat box, if any.
Chat box, I think it is disabled. Is it, or is it enabled for everyone? Sakshi, can people chat, or?
Let me check.
Because what happened is the previous speaker I saw, it was disabled. People were not able to chat in chat window. So I hope this is not the same case right now. Please have a look if anyone has any questions. Yeah, I can type message, but I'm not sure if others are able to do that.
I have enabled the option now. They can chat there.
Okay.
Participants, please feel free to drop your questions or thoughts with sir, if any. Till then, sir, I would like to share a few queries for further understanding from you now. Like
Sure, go ahead.
how can emerging technologies be scaled and localized to ensure real world impact for small and marginal farmers while remaining economically viable and sustainable?
So I think that was answered in one of my slides, where we are talking about enabling the digital to the last mile. So where we want to ensure that the farmers, all the farmers, have access to the digital interventions, especially the digital extension of advisory services, the mobile advisory apps or video learning platforms, SMS services, and e-commerce platforms. So that has to go till the last mile. And that is how the small farm and marginal farmers can also benefit out of that. They may not really benefit from drones and satellite imagery intervention, but yes, definitely with SMS service and similar mobile advisory apps, they will be able to get that benefit, subsidies and other things. They can take benefit, and they are taking benefits. I think that intervention is being done right now at this point of time. Sakshi, yeah, go ahead if you have any questions.
Sir, there are some questions in the chat box. You can see up to them.
Okay, let me see. All right. Okay. Oh, I see. One question is, how is AI used in pulse production? Uh, so I think that part we covered. So different kind of we can variety of developments, plant breeding and genetics through precision farming and crop management and post-harvest quality control. Those kind of things we can do using pulse production. Then question is, we talked about plant virus. Please elaborate. Okay. So in one of the screens, you had seen that by looking at an image of a plant, you can, there are machine learning algorithms. So every disease is being mapped. We create parameters. So a particular patches, the way the disease spreads, that identification is done by the machine learning algorithm that this particular disease is either through a virus or through a fungus or through a bacteria. So that detection is being done because we do reinforcement learning, we enable the machine learning algorithm to be able to identify particular the plant virus, and after that the required tech interventions is being done by looking at that. How AI is used in pulse crop, which parameters are being monitored? I think I just spoke about it. Precision farming and crop management through predictive input optimization or early disease pest detection, automated machinery, or smart grain storage through post-harvest, automated grading, supply chain optimization, and yield market forecasting and things like that. This is what we spoke about. And I think Rajeshwar Shelke says, no doubt AI is future for precision farming, but how can we apply it in livestock management at local level, because they have very small herd. See, if there are very small herd, you may not require it, but if the herds are larger, see what, for example, if you are doing poultry farming and you want to make sure that there is no disease spread happening among the chickens. So what you can do is you put in some cameras and some sensors. The sensors will be able to detect the different heat, and if there is any other specific chemicals around it, or by looking at the image and the processing the image, you can figure out if there is one chicken which is got a disease and bird flu or stuff like that, it can spread across, right? So that AI intervention can be done. If it is very small stock, then you may not really need it, but if at all you need it, so I gave you an example of poultry, it can be applied to sheep herds and others as well. We see a lot of predictive AI models for crop health, but grounding truth remains a challenge in our experience. What is the biggest barrier to getting farmers to actually trust an algorithm recommendation over their own intuition? It's as simple as this. Here, whenever I go out, I check at the weather forecast, because I'm not sure whether there will be a snow, snowstorm or anything else, whether my vehicle gets stuck somewhere because during the winter. So I will either trust the weather report, or I will go by my intuition that the sky looks clear to me, so nothing can happen. But if I look at it, could say that in 1 hour I'm going to have a snowstorm. So either I trust the technology or I don't trust technology. So it comes down to the awareness and percolating down the knowledge and the public-private partnership, that how things work and how things gets improved. Okay, so So ground truthing, it's I think a lot of public and public sector as well as private sector partnership can only do it by educating the concerned farmers. That is the only way. There is no other way. Through different multiple channels or multi channels, so through internet, through television, through radio, and through communication through person-to-person communication and similar things. Then I see Dr. Joyarani Pegu. How IoT and AI be used in mushroom cultivation? See, in mushroom cultivation, again, it requires a specific environment. It grows in moisture, and certain moisture content should be there, certain warmth should be there. So all those conditions can be calibrated in your sensors. So if there is a change of the same, then you will get SMS and alerts so that you can come and do the required intervention. Otherwise, the crop get damaged. Okay, so that is one of the things that you can do. And whatever the IoT, when we say IoT sensors and IoT cameras and stuff like that, all that intervention are data proofs that AI processes. So AI is how it works, the machine learning algorithms. Okay. How to validate our data generate by AI is accurate data. See, there will be nothing will be 100%, as I showed in the previous example, where machine learning algorithm tells you that, okay, this is a fungal attack, 98% it is a fungal disease, 98%, but 2% it's not sure. Okay, 95%. I will tell you one of the use cases I remember. MSP, I think all of you know, minimum support price, right? So there was a minimum support price guarantees what I think a lot of state they demanded to the central government and stuff like that. So there is good and bad thing both to that. Good, of course, most of the farmers, they benefit out of that, and there is always a leakage also out there. For example, in certain states, in some of the states, the farmer, just to simplify what is MSP for anyone who doesn't know, if a particular crop cost market price is 100, the government guarantees that it will buy in 140 or 130. Okay, as an example, it's not exactly that price. So that helps the genuine farmers. But there are also some smart people who are not genuinely, they don't have a genuine farmland. They will declare that they have 5 acres of farmland or 50 acres of farmland or whatever. And this is the paddy that they have cultivated, and they will sell it to the government. But in reality, that farmland could be a pond. It could be just a plain barren piece of land. And they would have bought from the market and sold it to the government from another state, same state or somewhere. And that was done in some of the, I think that was very prevalent in some of the states. And one of the state approached our organization, and we did a tech intervention when we took satellite imagery, processed it. We figured out that which of them was a pond, which of them was a farmland, which of them was actually paddy, and which of them was mangoes. So we processed that, we shared it, and I think we got a success rate of around 95%. And as I said, there is always a percentage of error is there. So that percentage of error, the physical validation was being done, and one inspector went and physically saw that whether it was paddy or not. So in some cases, a pond, which was declared as a pond, could be actually a paddy land, because a lot of irrigation, the water comes up and it looks like a pond for the image, satellite image, right? Again, there is a question that the inspector who goes to do the review can also get compromised. Yes, they can. He or she can get compromised, and that is where we also came up with a mobile app, wherein the mobile app will take an image only when you are in that 5 meters perimeter of that particular field, and it will send a real-time timestamp of latitude, longitude to the server that yes, this is the correct image at this point of time. So we had done that, and that particular state, they were able to save thousands of crores in otherwise would have been gone to for the wrong persons in the MSP. So it should go to the right person. That's a good thing. Go to the wrong person, it is not a good thing. So that's what we had done as a tech intervention. Just answering the question, that previous question on that. It started with the AI accuracy, but then yes, AI can hallucinate. So we have to keep calibrating it and getting it better and better. Next question is, you have talked about plant virus. Can you name some of the AI tools for plant virus? There is no such, there are companies and products. The the tool is not like ChatGPT or Gemini or some. It's not a tool as such. And there are some products and some market brands which is available for different, say, to figure out. And that there are tech interventions that is done by SI companies or system integrators. The companies, they do that. So one of my previous organizations, CSM Technologies, they also do it. So there are many companies which does it. Next question, any possibility of integrating AI in managing climatic parameters related to mushroom cultivation? I think I already answered that. Yeah, it's there, identified. Utsav sir, how we can reduce carbon footprint, and it is only a single solution for planting more. See, carbon footprint is not just planting, it is also our habit of what we are using. For example, those who do shave by the spray, spraying of your aftershave, not after, I mean, shaving lotions, that also brings a lot of carbon footprints. When your systems, computers are running, which is not switched off when it is not required, that also produces a lot of carbon emission, right? So carbon footprint is not just planting trees, it is also not doing things which harms the carbon. And all the companies, they can contribute to it, organizations, say even IT companies, because IT companies produce a lot of carbon footprint because of the heat generated by the CPUs, by laptops. So what they can do is, IT companies or say manufacturing companies or plastic company, they don't have to plant, of course, plastic companies has to be generate plastic only when it is really, really required. But what I'm saying, coming to is manufacturing companies, IT companies, financial companies, what they can do is, there is carbon credits they have to buy. So they are not doing a planting, but they can buy the credits from a company which does the planting. So basically what they do is, if they buy, say 100 carbon credits for 100 trees or whatever the number, I'm just giving a hypothetical number. So the IT company gives money to that plantation company and gets a credit or carbon credit for those that, yeah, we have given the money for planting 100 trees. And that planting company, whichever is registered with the government, shares the data with government. That way, they show how much of the companies are becoming carbon neutral. Carbon neutral is when you are emitting as much as you are absorbing the carbon monoxide from the atmosphere. That is carbon neutrality. And that is what everybody can achieve. Ajeshwar, thank you. Yes, thank you to you too. Which digital tools are currently showing the fastest return on investment for mid-sized farmers? For digital tools, see, I think nowadays drones are being used a lot, and there are, in the past it was not being used. And I think sensor-based, even tractors, they have a lot of IoT fixed tractors is being used. That also has asset management and fuel management on that. And then there is some IoTs fixed in for the farm monitoring, stuff like that. Without a standardized data set, model can't work as desired. Sir, may I know, please, any standard data set working as of? See, so there are millions and billions of data and trillions of data sets across the world. Every use case is unique, every data is unique. So every case study is unique because it applies to that particular field. So that will be unique. So for that particular field, okay. We'll go to the next one. Any collaborative activities going on in this direction to build standard localized data sets? Can anyone join the activity? Building data sets, it's a very generic term. Data sets can be of everything. Livestock data set, farmer data set, land data set, mango data set. So there is no such standard data set. It's not 100 people sitting at one corner doing data set building. They are not doing that. So it is only project specific, that what is the purpose of the project and objective, and accordingly the data sets are prepared. Please share the email ID on which we can contact you. Okay, all of you can contact me. See, email ID I'm not very on, but I will write my LinkedIn. Okay, linkedin.com/in/ Nilabdi. So this is where you can send me your connections. I will accept it. You will have any questions, you can ask me. Okay, this is I have just pinged. And if you still want to email me, you can email me. I will just write it at labdi@gmail.com. You can send me. I don't check the emails as frequently as check if there is a message in LinkedIn. So you can send me a LinkedIn message. You can send me connection. I can accept it. I do a lot of talks also, and there is any specific question, I'll be happy to answer that. I think I don't see any more questions. Sakshi, anything else for the
No,
day?
sir. It's done for today. Okay, thank you very much, sir, for patiently addressing all the questions and clarifying our doubts, and for delivering
Okay.
such an enlightening, engaging, and thought-provoking session on tech interventions in agriculture. On the behalf of Just Agriculture and Indian Society of Agriculture Science and Technology Research, our collaborating institutions, and all the participants of the International Winter School Training Program, I sincerely thank you for sharing your time, expertise, and valuable insights with us. Your presentations help bridge gap between innovation and on-ground application, making complex technologies understandable and relevant to the diverse stakeholders. The perspectives you have shared encouraged us to rethink traditional approaches and envision agriculture as a technology enabled, sustainable, and farmer centric system. Once again, thank you for being a part of this prestigious program and for contributing so meaningfully to the success of this program. We truly appreciate your valuable contribution and look forward to applying the insights gained today toward building a resilient and future ready agriculture ecosystem. Thank you very much, sir, for truly enriching sessions with today. Thank you.
Thank you, Sakshi, and thank you everybody else, whoever have participated. It was great. Thank you.
Thank you, sir.
Somebody says Vikas group chat was disabled for you. Okay, I'm sorry about it. You can send me a message. I will be happy to answer you. You have my email. You have my LinkedIn. Anyone want a question? Send any question. I'll be very happy. I'm pretty active in LinkedIn, so you can use the above link and we'll talk there. Okay. Take care, all of you. Bye bye.
Yeah, thank you, sir.
Just exit.
Okay, thank you everyone for being a wonderful and engaged audience. With this, we come to the conclusion of day 20th of the 21-day International Winter School Training Program. We sincerely appreciate each one of you for active participation, your thoughtful engagement, and enthusiastic presence throughout today's session. Your energy, curiosity, and eagerness to learn have truly enriched the program, making today's discussion both impactful and intellectually stimulating. Sorry, we extend our heartfelt gratitude towards our esteemed speaker for generously sharing their experience, expertise, and valuable insights, and to all the participants for their meaningful contribution to the success of today's session. As we move forward, let us continue with the same spirit of enthusiasm, positivity, and commitment. May the knowledge gained and connection built today inspire innovation, collaboration, and purposeful action in your academic and professional journeys. We look forward to your continued participation in the upcoming sessions as per the program schedule, where we will continue to learn, grow, interact, and exchange ideas. Once again, thank you for being such a dedicated and inspiring audience. Wishing you a pleasant and restful evening. And we look forward to connecting with you again very soon. Until then, have a very wonderful evening.